Hello and welcome to the course CNN with Residual Connection, ResNet. In this lecture, we are going to introduce residual network or ResNet. Then we discuss what is the residual connection, formerly known as skip connection. And then we try to understand why skip connections are advantageous. And then we discuss the ResNet architecture. So far, what we have discussed that the different CNN model, we start from different AlexNet models like AlexNet, then VGGNet, this is the VGGNet, then GoogleNet. Now we going to discuss another very important convolution neural network. It is called ResNet or a CNN with residual connection. And you can see here the number of layers is very high in comparison with its previous layer or previous architecture like GoogleNet. It was 22 layers. Now it can go up to 152 layers. So it's a huge jump. And error rate is also more or less half. So this is very important milestone that has been laid in 2015 by virtue of proposing this ResNet. Today, we are start understanding what this ResNet is all about. Okay. Now, what we have seen so far, that what are the challenges of deep network? What we understand that vanishing gradient is one of the major problem that we have to solve. Other optimization problem that kind of make the network harder to train, or network fails to learn identity mapping, kind of covariate shift kind of problem. Overfitting is also. So some already we have said the internal covariate shift and this kind of optimization problem of identity mappings. So what we have seen, there is a different problems, but in this particular module or this part of this lecture, we are how to solve, because this is a very important problem that we have to solve. Now we come to a very known that we have discussed this previously, that what we have seen before, that there is a some sort of attempt is made to reduce the vanishing gradient problem by using leaky ReLU. It definitely reduces but does not eliminate the complete vanishing gradient. Because of these negative inputs, this gradient is small but non-zero. And during back propagation through many layers, these gradients are repeatedly multiplied, and this causes the exponential decay of the gradient loss. So as a result, what we have understand that this kind of activation function, even it working to some extent, but not fully solves this vanishing gradient. There is the other reason that we have discussed. Basically, this leaky ReLU is basically proposing to solve this gradient decay, this kind of problem, is address the dying ReLU problem, and there is a cumulative gradient decay, so on. So leaky ReLU do a good, but it's not enough. So to effectively address the vanishing gradient problem in a very deep network, architecture such as residual network is proposed, and that is the topic of today's lecture. and what we understand, what do we mean by skip connection, and how skip connection allow gradients to bypass one and more layer. That we'll see in detail. And this bypassing procedure actually preserve the gradient flow, enabling the successful training of much deeper models. And that is that we discuss today's lecture. To solve this vanishing gradient problem, in 2015, ResNet has been proposed. Now, what actually this ResNet is all about? ResNet, basically pulled from the Residual network, it's a deep convolution network that we have seen that it goes up to maybe 152 layers. And it basically can deal with the vanishing gradient problem even with this very high depth. So that addresses the degradation problem encountered when training very deep networks. So what is the major innovation in residual network or ResNet? Is that to handle this vanishing gradient problem if network depth is very high. Now it introduced a kind of concept, it's called residual learning. I'll come what is this. Through a hardware, it's called skip or shortcut connection. So skip connection is a basic, a very simple idea by which we enable the residual learning, and that makes this ResNet to mitigate the problem of this. So what actually do that allow this particular residual learning via shortcut connection or by skip connection, allow the input of residual block to bypass one or more convolutional layers and can be added directly to the blocks out. That we will see in detail when we the architectural understanding. That is how this bypassing is helping for the gradient decaying. So if you try to understand that instead of learning a direct mapping, normal CNN, even in GoogleNet we have seen there is no this kind of connection is there. Ultimately it's there is an inception model, but there is a direct mapping. You can see in VGGNet, in AlexNet, all that. So unlike this direct mapping, in this ResNet, that network learns a residual function. That we have to understand. What is the residual function? And this enables this particular network more effective gradient propagation during that propagation, which mitigates the tension gradient. So 2-3 things what we have tried to understand in this particular module of the lecture. That what do you mean by residual learning, or how residual learning is being done by simulation function through a hardware called skip connections. Now, as a very naive discussion, that this particular ResNet has a different variants. ResNet 50, which is 50 layer. ResNet 101 is 101 layers. It's 152, it's 152 layers. You can understand that how many layers. It's a very deep network. And in computer vision application, definitely, so without vanishing gradient problem, if we come up with this number of layers, it's a very powerful feature extractor for tasks including image classification, object detection, semantic segmentation, instance segmentation, image vector, and so on. And even we see that this ResNet is also being used in a different application like medical imaging, like this weather forecasting, and many more. That is the now what actually it helps, since it's a very deep network, hierarchical feature representation is very robust there. It is very scalable. You can understand this 50, 101, 152, and compatibility with transfer learning have made it a foundational backbone of numerous state-of-art computation systems. So ResNet, that's why, since it has a huge depth or huge and deeper network, and it make a revolution in the computer vision, as well as we'll see in the later generative AI also. So as a whole, this is the very basic or just introduction of this ResNet. Okay. Now, here we're going to understand what we mean by skip connection. Now, we can see here that is the plane network, the normal CNN module. X is input going to a convolution layer, then ReLU or something non-linearity is attached here, and then another convolution layer I got Hx. So from X we find Hx. So we can map X to Hx, which Hx is the function. Now, what in ResNet do? It add a kind of bypass connection, and this connection is called skip connection. Now you see, this is more or less same, but there is the extra connection put here. Okay. Now this Hx for this ResNet. Now what is this? This is what Hx here. That now is fx plus x. Now this is fx. Here we actually model fx here, and now hx we can see, or we can write this fx plus this x. So the question is that what ResNet is basically in this, basically going to this model, or going to model that fx. So ResNet learns the residual mapping that fx is hx minus x. So one thing you can understand, it is a complete mapping hx, but here for ResNet we map some bit simpler because minus of x. So fx represents the difference or residual. The fx is the residual between the input and the desired. That residual we are going to map only in case of ResNet. So learning only what needs to change, that fx, is often easier than learning the entire transformation from scratch. That is basically the importance of skip connection, and it has a very interesting or characteristics or advantage, you can say, that if we say we'll see the vanishing gradient problems later, but here from the optimization viewpoint and the convergence viewpoint, now these residual blocks are basically learning more simpler function than the normal case. So definitely the convergence is more ready or easier to learn. So the optimization is much easier for ResNet. That is a certain advantage that we can figure out from this skip connection. And that is the essential importance or the basic idea of skip connection. Okay. Next, what the other advantages we get from skip connection? Now we can see our a complete residual net or ResNet is look like this. This is a plain CNN. You can see from image to classifier. Here also a image to classifier, but this skip connection. It can two module. It may be more than that or less than that. So there is a keep connection. There is a keep connection. There is a connection. So this is the basic idea of what is keep connection look like for an entire network. Now, first point is by providing a direct pathway for information and gradients to flow across layers. Now you can see here what is happening. From here, there is a direct connection with bypassing these two modules. So there is a direct connection apart from this modeling. When we thinking from the reverse side, backward side, there is a direct backward pathway. Okay. So that is the direct pathway from information and gradient to flow across layers. It is not only giving a forward path, it works in the backward, person is in the backward, person is backward. It's a connection that basically not involving in between layers. Okay. So skip connection effectively mitigate the vanishing gradient problem, allowing the stable training for validity. You understand? Because this connection is there. We'll see in more detail here, but at least we can intuitively understand that the gradient flow can go in this path, not from this path. If it goes this path, there is a two different multiplication kind of the gradient multiplication or is there, and it generally decaying the error gradient. But in this path, there is no such multiplication. So it's the direct path. So from here another direct path, from here another direct path. So gradient sum being live even from this. So that is basic idea of skip connection. I repeat this line that by providing a direct pathway from information and gradients to flow across layers, skip connection effectively mitigate the vanishing gradient problem, allowing stable training for variability. Now here also another thing. There is the identity mappings. Identity mappings means what? That what is the we got the input here, that is the same input there. So essentially this kind of connection enables networks to learn these identity mappings. Apart from this, if these layers is not that much important, then this is going to identify. So when additional layers are unnecessary, so when these are unnecessary, simplifying the optimization process and preventing performance degradation as network dependencies. That is very important concept. Because why identity mappings in come here? Because you see this is coming here. So even if it is not necessary, it will come here. So it just is doing as the identity mappings. So if it's not that much important, the identity mappings through this skip connection, simplifying the optimization process and definitely preventing performance degradation with a very deep network. Now, what we said earlier, it also accelerates the training convergence. Because of here, we are only model that hx minus x rather than whole hx that we have seen in the last year. So here the accelerating convergence facilitating faster gradient propagation. Furthermore, the skip connection promote the feature reuse. That is also a very important aspect. Now you see here what is happening. It is a feature extraction through this layer. Now, one thing is that this kind of feature extraction give you some kind of a different level of abstraction feature. But what here this feature? Just for example, it's an image. Or here, what is the feature? That feature is not similar that. But maybe this feature is also important. So that kind of reusability is being done due to this skip connection. So keep connection promote the feature use by preserving useful low-level and intermediate representation throughout the network, leading a richer feature extraction. So you can say that this low-level information is also propagating. These are very high level, these are high level levels, but this low-level information. So it makes the feature extraction much richer, much robust. So their architecture, because this ResNet architecture in this way, provides implicit regularization. And implicit regularization, why? Because using this kind of, because we are not only doing this feature extraction, rather we give some sort of actual here also. So this implicit regularization, which can reduce overfitting, improves generalization. So collectively, this advantage makes the skip connection essential for training deeper, more accurate, and more robust neural network at a wide range of computation. And that is the major advantage of skip connections that is basically used in the ResNet and make ResNet is a very valuable or very robust deep neural network for different computation applications. Now, if we see that what we already have seen, that is normal CNN nodes. L is input. Now this is this Z of L1. We put of A, we get AL plus 1. And again we put this layer. Now what does this mean? Now as we know very in our early discussion, that Z of L plus 1, this is what? This is the summation of this bias term B of L of this as so weight is basically multiplied with AL and we get this. So WL plus 1 A and we can get this plus we we can get this. And over this Z of L plus 1 we put a nonlinearity, it may be ReLU, it may be super anything. We can get this. So that is the normal Z. For the similarly ZL plus 2 is WL plus 2 of into A of L plus 1 plus B of L plus 2 as the normal. That we have the normal our neural network equation and we get the nonlinearity over this, we get it. Okay. So this is the normal case. Now, what it is the skip connection? Now, skip connection, it is similar. It is AL plus 1, Z of L plus 1. That's all are similar. But when we do this AL plus 2, that is not only Z of L plus 1. Here it is only Z of L plus 2. Apart from this, there is a connection here. This is, that is A of L. That is being added to this Z of L plus 2. And then we put a kind of activation function. So that's exactly that what we have seen in the previous slide. This is plain CNN and this is the mathematical understanding or kind of mathematical expressions to understand what this skip connection doing. Okay. Now come the how it affects vanishing gradient concept. This is bit involved. As you recall that what is vanishing gradient problem? That here this is the simple thing, that this is the forward pass, this is the back propagation. What we generally do, this is the y, this is the output, and we get this. Dy is basically half of d minus d square. Okay. So the idea is basically this. This is error gradient is first we calculate here, and for every steps we are keep on multiplying with this. So what? This is the normal back propagation. When these derivatives are small, the gradient signal progressively diminishes as it back propagated. You see, this if these are small values, that this when we propagate from here to here, when we going to a reaching the initial layer, the error gradient become very close to 0, and that is the basic problem. And it is basically happening because these derivatives are small. And we have seen in the last lectures very detailed of this concept is very this concept in deep. So this is the validation. Now how we are going to solve it? Now here how skip connection helps this vanishing gradient problem. Now what a residual block computes, that y is equal to fx plus this fx plus x, this is now y. X is input, fx is the few convolution there. Now here you can see that y is equal to fx plus this is the residual block. That this is fx and this is x plus x that we get. And that's why this is initially counted hx. So fx is equal to hx minus x. So this is basically it. Okay. Now you try to understand how this identity mapping or this skip connection helps. So gradient through with a skip connection is now in this way: del of L, del of y, the del of y dx, del of L, del of y, del of fx plus x. What is this? Is y. Initially it is hx, but now it is fx plus x. Fine. So what is basically this dl of L by dy or dl of fx plus dx plus 1. Now this 1 is very important. Why? Even if this is very small, that was the basic problem. If it is very small, even close to 0, the gradient has a direct path by this dl of dA because of this. So in this way the gradient doesn't vanish. That is very important to understand, because if this question, so why skip connection help solve the gradient vanishing gradient problem, this is the basic answer to this question. Okay. Now we are going to understand another very important concept, how skip connections basically enables identity mapping very easy for this ResNet. Now for that, to understand this particular phenomenon, identity mapping, what first of all, what is identity mapping? Let there is a base network. This is a x is the input, a of L is the output. Now here is two additional network layer. So these extra layers with skip connection. So these additional layers that is actually done in case of ResNet. Now, you see, if there is for a second, if you imagine there is no connection. So, identity mappings meaning that these two layers is basically non-functional. Okay. Now, here, what is basically is done by this script connection. This AL is coming here. Okay, this AL plus 2. That means basically. Now, we have to understand how. If we go by, let for this, there is no skip connection here. Okay. Now, here what is we are basically this Z of L of 2 is WL plus 2, AL plus 1 plus BL. That is the normal case. Now, what is AL plus 2 here? This AL plus 2 is now Z of L plus 2 plus AL due to this. So, if we put it Z of L plus 2 here, Z of W of L plus 2, AL of L plus 2 plus 1 plus A. So, this is due to the, if there is no connection, this AL is not. That is the basic idea of skip connection. Now, what happened? If WL2 is 0 and BL2 0, so this 2 here is not that much necessary. So, this makes it's what? That makes it nullified. If we don't want to use it, or that's not very important, then WL plus 2 and BL 0. That means this. But then what happened? This AL plus 2, that is becoming G of AL. That what exactly we want as identity mapping. So by this demonstration or illustration, we can understand how this skip connection to help make this identity mapping very easier for ResNet. So we can see there is several advantages of skip connection. First of all, the faster convergence. As we have seen in case of ResNet, we are modeling the function fx, that is basically hx minus x. So hx is the complete function, but here we rather modeling the entire thing, we only model the residual, the difference between hx and x. And definitely due to this skip connection, that the gradient flow is faster, or better gradient flow make the convergence faster. That means the faster training, the faster convergence. And it's not that much sensitive to initialization, because initially for making this convergence very faster, we have to deal with this the parameter initialization very judiciously. So all these things are not that much different because of this, and definitely more stable training. Next thing is the better feature reuse. Now, one thing is very important that we have understand that again we go back this particular figure. Now, what a deep neural network do? These initial layers basically model the very primitive geometrical features. They are not modeling the entire image, but is a very primitive or very low level feature. When we go in deeper layer, they are keep on model the more and more the complex feature. So feature extraction done in a different level of abstraction, from lower level to higher level, from the very primitive things to a very complex. kind of feature extraction. But one thing is very important. We understand these features is very complex feature, is very useful, but still we may be requirement some this kind of, just for example, if we say these are the very edges or textures are very rough or kind of, is very naive or primitive features. But here it is a more complex kind of object. But these are also important for classification. So this feature, if we add in this way here, these features are not lost even in the very higher layer. These primitive features still in these images still are there. That is feature reuse. This feature is extracted here. This feature is come here. This feature is, so that is some sort of feature use. And they basically don't kill this kind of initial level features at the higher level. And that is basically, we basically saying that reuse the low level feature is very essential. That preserves the spatial information because in image itself, and it drastically improves the performance in mission task. So better feature reuse is a very important contribution of skip connection in the ResNet architecture. Next come the regularization effect. How it easy or how to make it easy to avoid overfitting. So skip connection is what? If you see it from a bit different viewpoint, skip can make the network behave like a many shallow networks. Because it actually is what? It is doing some sort of kind of skipping. So this within a skipping block or within this is a shallow. So a small shallow networks are kind of some kind of thing with this. And if you do this has an effect to improve the generalization plans of data. Because it basically is a different number of networks. Okay. So different kind of more and more different network we are using, more the generalization we get. As a result, it helps to reduce overfit. That we have said earlier, but now we can understand it much in depth. So why this skip connection has a very positive effect on regularization to improve the generalization and to minimize the generalization error for unseen data. Okay? And as a whole, that is very robust to the network depth. Now we can say if this kind of issues, the convergence issue, feature usability issues, then regularization issues, vanishing gradient issues, definitely that the deeper network can now be more and more powerful because these problems, vanishing gradient problem, feature usability problem, regularization, make the deeper network not that much effective. But if we solve these problems by skip connection, that becomes more and more efficient. So skip connection allow additional layers without causing optimization. That also is faster convergence. This reduces the risk of vanishing gradient, makes a deeper network easier to optimize. That also we have seen in our previous discussions. It facilitates the design and training of very deep architecture and add no trainable parameters or complexity. So without this that skip connection, there is no extra parameters is required. So these are the basic advantages of skip connection, and that make all the difference. Now with this background, we now try to look the entire ResNet model. So this is actual the ResNet. Okay. So what this ResNet architecture is? ResNet architecture is facilitated efficient gradient propagation that we have seen that this by virtue of this skip connection that mitigates the vanishing gradient problem, that also we have seen, and enables the successful training networks with depths 50, 101, 152 and even more layers. So as a whole it looks like this. And if we take this 3 cross 3 count 128 in 120, this is basically one skip layer. You can say this is a skip connection. So here x2 this fx plus x, that here we can say y, that is initially we thought it's hx for the plane network, but not for y for notational convenient consistency. Y is equal to fx plus x. So essentially the residual mapping or residual understanding or modeling, residual modeling. So this is the basic block, and this is the one module of ResNet, and this kind of modules and are basically keep on adding to get the entire network. Okay, so we begin with a convolution layer. So we begin with a 7 cross 7 convolution layer. It's a 7 cross 7 convolution layer with 64 filters. Okay, and with stride 2. That strides 2 we can understand. What is stride? That we go 2 pixels ahead when right side in the bottom side, because with our convolution kernel or semi kernel we just keep on slide this convolution kernel over this kind of image or image patch. Now stride 2 means every time we jump 2 pixels in right direction or bottom. Okay. So it and a typical ResNet architecture begins with a 7 cross 7 convolution layer, that is 64 filters with stride 2, followed by a batch normalization, that you can say that is the batch normalization here, and ReLU activation function, and a 3 cross 3 max pooling, that is the. So here after that is a batch normalization and nonlinear activation used, and we can then use the pooling. So this is the very initial. After that, what we'll basically do, the network is then organized into 4 sequential stages. Absent 3, so there is another stage here. So 4 sequential stages of residual blocks. You can get this is the 4 sequential stages of it, where each stages extract increasingly complex features while progressively reducing the spatial dimension through strided convolution. Now, first of all, what do we mean by strided? We already said that strided convolution means how many pixels we are jumping when our convolution kernel is being just slided through the image patch or image. So that in this case it is the strided convolution means what? If stride is high, definitely our dimension will be lesser. So that is the basic meaning of stride. So it basically that increasing the complex feature while progressively reducing the spatial dimension. Not only that we extract increasingly complex features, but we reduce the spatial dimension to the strided convolution. So that is the another feature. Now what we have to understand here very carefully in that this is after these initial layers, this how these kind of skip connections are basically using, and by virtue of this skip connection and what this Now it may be a, let's say it is a 50 network, a 50 layer in between this. Now, one thing we have to understand, even if it's a 50 layer, this deep connection is this efficient gradient propagation. So from here to here. And that is the basic understanding or basic advantage of skip connection. Not only that, the feature reusability that we see, that this features is live here, also live here, also live here. In this way, the feature reusability is there. The faster convergence, because this here you can see this fx is much smaller than full is fx is y minus x, then full y is this. So we can only here we model the fx. So the faster convergence and so on. So these are the basic understanding. That's why ResNet. After that, and the full ResNet architecture, when it completing with, there is one another important thing, that is the final residual stage, the global average pooling, that aggregates the feature maps into a single feature vector. That is the global average pooling. There, after the last convolution layer, this is the global average pooling that aggregates the feature maps into a single feature vector. That means the global average pooling, which is passed to a single fully connected layer. This single fully connected 1000, because it's the ImageNet challenge, followed by a softmax classifier for prediction. So it basically that these are the basic steps of completing this. So this in this thing, that the global average pooling that aggregates the feature maps, single feature vector. Then there is a fully connected, a single fully connected layer, and followed by a softmax. So this basically thing, and through this connection in between. So you can say in shallow variants such as ResNet 18 or ResNet 34, the basic residual blocks contain 2-3 cross-T convolution layers are used. Whereas the deeper variants, 150, 101, 152, employ the bottleneck residual layers consisting 1 cross 1, 3 cross 1 cross 1 convolution to improve the computational efficiency. Now this is also another thing, and for very deeper network, they use, we understand what is the bottleneck residual blocks, that what is the essential of one to one block, one by one block, that how it is used to improve the architectural efficiency, and then this convolution to improve the computational efficiency, we can understand. So here you can say total depth depending on this, that is maybe 34, 50, 101 or 152 layers for the ImageNet challenge. So this, apart from the shallow variants as ResNet 18 or ResNet 34, the basic residual blocks containing these 3 cross 3 convolution layers. Okay. Where deeper network is this kind of bottleneck layer for the more improved computational efficiency. So now when to this residual connection, to summarize here, that ResNet achieves a very high accuracy while maintaining a stable optimization. That is very important. Even if it's a 150, now we can understand the performance boost there. 152 layers even very efficiently, what very high kind of accuracy. ResNet has a high accuracy while maintaining the stable optimization. Even of this number of layers, the optimization is not compromised. It's a very stable network with maintaining the stable optimization, and making it one of the most influential architectures in text as image classification, object detection, semantic segmentation. Now, one thing we say for this transfer learning, because This is very important concept that will come in details. But here, even after learning this, let's say we learn in a particular for ImageNet. This is the just image classification. Can we use this network, a very high 152 network or 101 network, for a different purpose? Let's say if it's a semantic segmentation or object detection. And here the concept of transfer learning, that this network is learned with a huge informations with image classification. And can this knowledge or this model be reused using a smaller data set, some sort of fine tuning concept to make it useful for a different objectives? That is basically transfer learning. And ResNet are basically very much used for transfer learning for very different kind of architecture. That's why it is said that ResNet is very useful for computer vision tasks. It's very efficiently using transfer learning. Okay. So here ResNet 50 and deeper bottleneck layers more efficient computation similar to GoogleNet. And you can see here 1 to 1 through 56 are projects, 56 maps. This is a residual block. This is the bottleneck layer. 3+3 concept operates over the only 64 feature maps, and 1-to-1 convolution filters project 64. So this is basically the bottleneck layers. What we have just said, that how this bottleneck layers is used for to improve this connection, because these 1-to-1 connections is used for this managing this kind of layers. So these 3x3s become very computationally efficient. And again we move to point to make it 256. So starting from 256 you get it to 56, but this costlier operation is done in only 64 channels or 64 kind of dimension temporal. This we can say 64 channels, and that how in this way that this ResNet 50 deeper and bottleneck layer used for efficient computation similar to GoogleNet. That this is the residual block with this bottleneck connections. Okay, so here you can say this is VGG19, this is 64 layer plane, and this is the 34 layer 34 layer plane network and 34 layer residual network. So as you see that this is the VGG net network for 19 layers. It is a 34 layers plane network, and this is what is the basic ResNet, and that is basic architecture of this, coming from 764 to these pooling layers and the average pooling, global average pooling, and after this maximums. So these are the basic idea of ResNet and how it improves with help of skip connections, where this feature reusability, vanishing gradient problem, faster convergence, many more advantages. So in summary, in this lecture we discussed about ResNet. First, we try to understand what we mean by the residual connection, popularly known as skip connection. And then we discuss why skip connection are advantageous and make this ResNet very efficient. And after that, we discuss the ResNet architecture in details. In the next lecture, we go into some other very popular model architecture based on the convolution neural network. Thank you very much.